remind me if I forget about this.
Really.
Hello? No? It's here. Okay. Ben? Can you...
Else I try to talk very loud. Okay, let me try this. So it can only get better. Can I take this? Okay. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open the session and I welcome you all to the public defense of Emma Bordier. Emma has presented to the faculty her PhD thesis on the topic on the origin of massive closed binaries and partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy, and astrophysics. Emma shall now publicly defend her PhD thesis. And Emma, you are invited to give a presentation of about 45 minutes about your work. Afterwards, our examination committee will ask questions and discuss your work with you. Before you start, I will briefly introduce the examination committee. We have here on site her supervisor, Professor Ruxana from the KU Leuven, then the co-supervisor, Dr. Abigail Frost, and online, maybe, Dr. William van de Wit, from European Southern Observatory. Then we also have online Professor Stefan Kraus from the University of Exeter. We have Professor Lex Kaper from University of Amsterdam online joining in. We have Professor Anne-Sophie Lubert from the University of Namur. And we have Professor Denis de Vrij from the KU Leuven. And I'm Professor Claudia Fleischmann. I'm chairing the session. Now the floor is you.
Okay. Good afternoon, everyone, and thanks a lot for being here, either in this auditorium or online. Today I will be presenting a bit of the work that I've been doing the past 4 years that involved observations at high umbrella resolution, with the aim to provide my piece of the puzzle in the big unknown that is the origin of massive closed binaries. Now, probably many of you don't understand completely that title, or maybe you understand part of the words independently, but when they are put together, then it becomes a mess. So I will start with explaining all the terms of that title, and then I will follow by the main objectives of the thesis and present the main results of my work as well. I really hope that at the end of this presentation, you can leave either this auditorium or close the app on your laptop with something you have learned. Okay. Good, it works well. So first, I would like to bring you back to this 11th of July 2022. I remember I was at ISO with other students and fellows in Chile, and we had for the very first time the James Webb Space Telescope release. So NASA, ESA, and also the CSA, which is the Canadian Space Agency, they made public 5 full-colored scientific images, and for the very first time by GWST. And we were waiting for that time. I remember I had just started my academic journey. So these were like the very first images we were really hoping for. So this is a stellar nursery. This is the Carina Nebula. And you can see like it has a bit of a shape of like craggy mountains on a moonlight evening. That's probably why I like it so much. And it represents the edge of urban, young, and strong region. This is where everything begins. It is in stellar nurseries, just like this one, that our sun was born 4.6 billion years ago, and consequently our home, that is Earth. We were born out of dust and gas, mainly, yes, just that. But you would wonder, how do we turn these huge amounts of gas and dust into stars? So these regions, where the density is a bit higher than the interstellar void, stars form from an small accumulations of gas and dust, which collapses due to gravity. So the dense and cold, it's very cold molecular clouds that are made of mix of atoms, molecules, and dust. They shrink under their own gravity. Thanks usually to an external source of energy, such as a little kick from a supernova or bucket molecular clouds colliding also with each other. And as the cloud gets smaller, it breaks into massive filaments and spherical pockets that you can see here. So this is like a filament and some pockets that we call clumps or hubs. And these hubs host dense cores of different masses, and these are the sites for star formation. Yeah, you can enter. Good. So in the traditional theory of star formation, the mass that is present in this curve defines the mass of the newly formed star. And in these dense pockets can be created one or more stars. If you create more stars, then we can call it a cluster. The newly formed protostar grows in mass through accretion at different scales. So it can grow from accretion from the envelope by like gravitational driven streams that we call inflows, but it can also grow from the accretion disk. So when you have like all the material that is collapsing from the envelope, you have to imagine that this material like collapses but also rotates really fast, and to conserve the angular momentum, then all of these flattens, and you have the creation of an accretion disk around the forming star. And from this accretion disk, there will be like streams, like spiral light streams, that will accrete all the material on the star so that the star can build up in mass. So over time, these nascent stars will use up much of the gas and dust from the original molecular cloud, though they may also blast some of it away in the form of jets or outflows during these very energy processes of accretion. The disk around these stars, so this little red part that you see here, is the place also where you can form planets that will become like the solar system in the case of mass stars. But in the case of massive stars, it's the site where you can eventually form other stellar companions. And then when the star or the central core here becomes hot enough, then nuclear reactions will be triggered at the center of the star, and a new star is born. So the formation process is over, and the star will start its very long journey until death. And at the time, the radiation is so strong that the star will blow away all the remaining birth material. Good. So now you already understand one of the terms, that is the origin. So by origin, I refer to the formation, actually, of stars. But what kind of stars do we actually form? Okay, so depending on the size of the molecular cloud, we may form a few to a few thousands, hundreds of thousands of stars. And there are like a plethora of different kinds of stars that we identify with a spectral type that are like letters that you can see here at the bottom. It's just a bit like you, when you were born, you were assigned a name, so name, weight, height, and this is how we know who you are and that you are unique. So it's a bit the same for the stars. And they differ by different things. First, there are stellar parameters, such as the mass, the temperature, the density, and in astronomy, we usually take the sun as a reference, always. So if we consider that the sun has a mass of 1 solar mass, then we will form stars as light as 0.1, even 0.01 solar mass, up to dozens or even hundreds of solar mass. And so we group stars by mass, usually in 3 different categories: low mass, intermediate, and high mass. And in the remainder of this presentation and in the thesis, and I think broadly all the massive star community will agree that we call the massive star any star with a solar mass that is greater than 8 when it's born. All these stars fall into this category, and all the rest for this presentation, I will call it low mass. We have this whole spectrum of masses, but given the limited amount of available material in the initial cloud, we will form way more low mass stars than massive stars, such that in the end, when you have a population of stars, only 0.1% of them will be of high mass. So they're really rare. So here you already understand a second term, if it wants to, yeah, here, which is massive. So massive stars are really important when we study the universe because they are powerful machines, and their study is relevant in a lot of different fields in astronomy. First, because the very, very first stars that were born in the universe were of very high mass. And they were known to have created very first galaxies and to have contributed to the reionization of the universe, which means when the universe became visible to us. Their study is also of great interest because they end their life in supernova. I will come back to this later. So that all the chemical elements that are created inside the stars are then spread away in the interstellar medium. And that way you fit this cycle of star formation, and all the heavy elements we are made of, all that you can see around you, all come from massive stars. So they're really important. And of course, they also hit the interstellar medium, and they can also trigger new phases of star formation. Okay, so if we continue with why we care about them and how they differ with their low mass counterparts, another thing that makes them very different is their formation timescale and lifetime. So if you look at the formation timescale, stars like our sun will take a few million years to build up and to be created, while massive stars, they form very fast, in about 100,000 years. So they are very much faster to form. That also like creates a problem because we don't know how we can amass such amounts of material to build such a massive star in such a short amount of time. And then for the time scale, so the majority of the life of a star is spent on what we call the main sequence phase. So it's a phase that they enter when they start to ignite hydrogen at their core. And it ends when the hydrogen reserve is over the core and they start burning helium. At that time, we consider that they are already entering the evolved phase. So the overall life of a sun-like star is estimated around 10 billion years. So we have time because the sun is 0.6 billion years old. While massive stars will live around 10 million years, more or less. So to conclude, if we all now decide to build stars, right now, and we build a low mass star and a star, by the time the low mass stars will be built, the massive star will already have gone through explosion and death. And this brings us to our next point, which is the final fate of stars are very different depending on their mass. So low mass stars will go through this red giant phase, which is what the Sun is going to experience in 4 billion years, more or less. And then also like go through this explosion and then that's a white dwarf. For high mass stars, we also go through this red supergiant phase, where during this phase, the star will lose a lot of mass through winds and radiation. And this is also a phase where like the interstellar medium is a lot enriched with the outer layers of the star, the chemical elements. It will go through supernova, and depending on the mass of the hot star, it will either create a neutron star or a black hole. And these objects are like different type of dead stars. Good. And an important feature that we're going to deal with the rest of the presentation is the degree of multiplicity of these stars. So usually, so multiplicity is defined as the number of observed central objects around which we can spot at least one companion. Okay, so if we look at the multiplicity across the rest of the masses, that is here on the x-axis, we clearly observe that the most massive the star, the most likely it has a companion, at least one companion. Indeed, like for all stars, it reaches almost 100%, and then decrease as the mass of the star decreases. And this is a rather recent statement. It's less than 20 years old, I would say, because before we did not have the sufficient observing capabilities to come to that very important result that affects the evolution of massive stars. So I was saying before, more than 90% of OB stars on the main sequence, so in their main phase, are found in binary systems. And the measurements go even beyond the partnership. We were even able to measure what is the period of the separation, more or less, around between these stars. And they found that 40% of massive binaries have periods of less than a month. So, for example, it takes Earth, a planet, 1 year and a few hours to complete a full orbit around the Sun. And these stars, they precess around each other in less than a month, with sometimes periods as down as a few days. So they're really close to each other, the period is really short. And this is what I mean by closed binaries. It's a system composed of at least two stars for binaries actually, and closed because their period is really short. Okay. And this has very strong consequences on massive stars, actually. This is a really not insignificant feature when we deal with massive stars. The life of massive stars will be disturbed and influenced by the presence of a close companion. So this sketch here depicted evolution for a single star, but this one, you see that it becomes so much more difficult when we add a companion, to the point that you might create a black hole or like a binary form of two black holes, and this will generate a gravitational wave. So I will not go through all of this. You can go during the reception. There are a lot of experts in this auditorium about the evolution of binaries. But it's just to tell you bottom line that the whole evolution will be affected, and then you can create what we call progenitors of gravitational waves, which is like a very vibrant topic at the moment. Good. So from different observational studies, we know that multiplicity appears early, very early in the evolution of stars. And that is not a property that they acquire during their evolution. They can by dynamical effects, but we know that even early in the evolution, they acquire this this characteristic. So several theories emerged, mainly from the theoretical point of view, to try to explain how we can form these massive binaries. So again, this sketch that I showed previously depicts the formation of a single star, massive star, but where is there space in this to actually form another companion? So there are different processes. One of the processes is fragmentation. Fragmentation is a generic term used to define the process by which self-gravitating objects develop substructures, and these substructures can evolve as a companion. And this can occur at different times and scales during the formation process. First, you can have very early during the formation process filament fragmentation. So these filaments here will fragment into two. They will create two cores that are very large separations. And fragmentation can also happen during the core phase. Here again, like this big core and these pockets can fragment and create two stars. And at the smallest you can form within the accretion here, you can form companions through a process called disfragmentation, and this is how you form close by companions. Good. And there is another channel that are the dynamical evolution. So the dynamical evolution is due to the gravitational interaction between bodies and do not longer depend on the gravitational collapse that depends on thermodynamics and fluid properties of the medium. So it's really like dynamical interactions between the bodies themselves. And for the formation of closed binary, physical processes that are most likely to play an important role are the migration through the disk. So you form a companion within the disk, and then there are like migration processes that will push the second companion towards the central one, and it will leave like a tight binary in the end. Another process would be you have the influence of another companion, so a second companion that is outer, and due to dynamics, dynamical evolution, this outer companion will strongly influence the orbits of the inner binary here to the point that they might end up as a really tight system. There is another process that we call capture, which is basically a star and a companion or binary system will attract another star that was not initially bound to that system, and they will come together and be bound for a bit of their life. Good. So this is exactly where my PhD project comes in. So now that you understand all the terms of the title here, let me introduce the main objectives of the thesis. So first and foremost, we need to evaluate the multiplicity in young populations of massive stars to know whether multiplicity is in fact, or if multiplicity, in fact extends to the earlier stages of a massive star. And by doing so, it obviously leads to our second main objective, which is to understand when and how exactly multiplicity is set. In particular, what are the pairing mechanisms that lead? Thank you, Nico. So yeah, it leads us to our second objective, which is to understand when and how exactly multiplicity is set during the formation processes. And what are the pairing mechanisms, so how we form multiples, and what are the observational imprints or signatures that could guide us towards one or another formation mechanism. So these questions, of course, are not addressed correctly, but we rather try to keep these three main questions as the driving line for each of the projects that are conducted. Good. So to meet these objectives, I will mainly rely on observations. However, just as mentioned earlier, the physical processes that lead to the formation of companions have different scales of action, which means that different observational techniques will be required, and because different observational techniques will trace different spatial scales around the star that we are observing. And of course, it will trace different physical processes, just as I showed earlier. So one of the processes we first want to try to understand or to test in more details is the inward migration that I showed you through the accretion disk. So how we can do so? A good proxy for inward migration is the presence of at least one or more companions, the expected size of the accretion disk. And that accretion disk for a massive star can extend up to 500 AU. So we want to test actually what is the companionship in this range here. And you see that it exactly falls into the use of long baseline interferometry. So this is what we use in the first project. Now, maybe this is even less understandable for you, so we try to quickly explain what is long baseline interferometry. Okay, so we astronomers usually choose the telescope and the observing technique based on the angular resolution that it can deliver. So the angular resolution measures the ability of a telescope to distinguish small details on a celestial object. It is defined as the theta here, which is lambda over d. So this parameter depends on d, which is the diameter of the mirror of the telescope, and the wavelength at which you're observing it. Good. So let's take an example. The human eye actually has a lens, is a perfect telescope. And we have here these very famous three rocks in La Réunion that are called les Trois Salas. And they are separated by more or less 10 meters. So the human eye has a resolving power of 100 arcseconds. Considering that the pupil size of the eye, someone that doesn't wear glasses and doesn't have any disease, is 4 millimeters. It can actually vary between 2 and 9. I made some research for that. So everything can be found in nature. So we wonder how far can we go? Like how far can the observer be so that it still distinguishes the two peaks and that it's just not a massive rock or massive shape that you would see. So for the human eye, at the limit distance of 20 kilometers, you can still see the two peaks of the mountain. And I did some calculation for my friends in La Réunion, if you go to the viewpoint of Cap Noir, you should still be able to see the two peaks. And if you don't, maybe you should have an appointment to the doctor. Good. Then, yeah, we have another very famous telescope that we use at KU which is Mercator in La Palma. So this telescope has a diameter of 1.2 meter and is operated by IVS in the Canary Islands. So here the resolving power drops to 4 arc seconds. So it mainly says that at a limit distance of 5,200 kilometers, the Mercator telescope will see the two peaks here. And then we go even bigger with the telescopes in Chile that have a diameter of 8.2 meters. So then this one is called the UNIT telescope, and is part of the very large telescope that is located in Atacama Desert. And for that one, at the limit distance of 35,000 kilometers, you will still distinguish these two peaks. And 35,000 meters, to have an idea, is almost twice the distance between the North and the South Pole. Good. Now, let's reverse the problem and look at what resolution we would need to perceive two stars that compose a binary system that are separated by 4 astronomical units. So I forgot to mention that there are some of the units equivalences. So one astronomical unit is the distance between Earth and the Sun. And this binary system is located at 2 kiloparsec, which is typical distance to find massive stars. So 2 kiloparsec, 1 kiloparsec is 200 million AU. Good. So if we want to look at this system at such a big distance, we need a resolution of 2 milli-arc seconds. And this corresponds to a telescope with a mirror of over 200 meters. And we know that we have some problem because we cannot build a telescope with such a big mirror. It would pose a problem for transport this telescope in the desert or whatever. We are not able to do this now. Maybe in the future we will. But then we still want to see this type of objects. So we have to find about an idea, and this is how the astronomers came with the idea of astronomy, interferometry, sorry. Astronomy as well, but interferometry. So interferometry is a physical process that was first introduced in the 19th century by Michelson, and wanted to combine the light of different telescopes to try to understand or to see the satellites and the asteroids. So you combine the light from different telescopes, 2 or more, in such a way to make this combination of telescopes act as if the mirror was as big as the separation between all these telescopes. And that way you will create a virtual telescope that has the size that you wish. And this is what was done in different places in the world. And for example, here I put the example of the VLTI, which is a very large telescope interferometer array in Chile. So this is how basically you build an interferometer. You have a telescope with a diameter of 8.2, and then you combine all of them, and the baseline is 200 meters, and somehow you can create a telescope of a virtual size of 200 meter diameter. Now, what matters is no longer, so as you understood, the diameter of a single telescope. The separation between these telescopes we call baseline with a B. So now the resolution of the telescope is no longer lambda over D, but lambda over B. And that way we can distinguish between two stars of a binary system that would be located at 2 kiloparsecs and with a separation of 4 astronomical units. Good, so this is a very nice picture of the layout of the very large telescope interferometer in Chile. And all the light of the telescopes is recombined in this lab here that you see. So thanks to like delay lines that are located lab under this platform, we use delay line to make all the beams interfere together, and then this is what we measure on the detectors. Okay, so if we use the LTI, then the two peaks of Les Trois Soleils could be distinguished at a distance of 1 million kilometers. It is 3 times the distance from Earth to Moon, also the distance between us and the James Webb Space Telescope, which is very far away. Now, if we decide we want to keep this VLTI in Chile, with such an interferometer, we can see the two peaks really well, but we could also see a chameleon that would be standing on top of one of the two peaks. Good. With all this information in hand, let's talk about science and the first project I conducted. So I looked at the multiplicity of young O-stars using near-infrared interferometry. So the choice of a scientific object was pretty obvious since we wanted to test the migration scenario. So we used this star-forming region here, M17, that showed very low radial velocity dispersion. So here the terms are more technical, but it mainly means that most of the binaries in these star-forming regions have rather large separations and periods. So M17 is located in the Carina Sagittarius spiral arm and is one of the closest, most luminous, and youngest star-forming regions in the galaxy. As I said, there is a lack of short-period binaries in that region, and hence is a good test for the migration scenario. So the sample is composed of 6 young O-stars in a cluster, a subcluster in this big star-forming region, and they are rather bright, of luminosity 5, meaning that they have just finished the formation process and have entered the originating sequence. We know that these stars already have spectroscopic companions. So what is a spectroscopic companion? It's a companion that is closer than 1 AU, more or less, in separation, very, very close companion. Good. Then how we detect young massive binaries. So star-forming regions are full of gas and dust, which act as a shield between us and the star in the visible light. You can see here, again, the example of the nebula observed in the optical light with Hubble at the top. And in the mid-infrared with the James Webb Space Telescope. And you clearly see more stars in the bottom image than in this image. For example, if you take the region here, in that mountain or this square here, you see that you can go deeper. It is the same for massive stars. So on top of being located in such regions, young massive stars are also embedded in their own dusty envelope. So we really need to observe them in the infrared to try to see inside this envelope. And then, of course, we want to resolve binaries from 1 milliarcsecond to 100 milliarcsecond to match the size of the disk. And we require interferometry for that. So we used the VLTI, the 4 UT telescopes, And we use the instrument gravity, which operates in the K band, so it's 2.16 micron. And with that interferometer, actually, it does not produce a direct image, but it provides the observer with two main interferometric measurements. So I will try to explain you quickly what type of data we get with interferometer. Most common measurement in optical and infrared interferometry is the measurement of the amplitude of the fringes. So as I said earlier, we will collect the light. So I just put two beams here, but of course it goes through the 4 telescopes. And then this light from the 4 telescopes is recombined in this beam combiner, and we get this interferogram here. And what we measure is the fringe contrast that we call the visibility of the fringes. So an unresolved point source will have a high contrast fringes and a normalized visibility of 1. For a spatially resolved star, which means that the theta, the size of the star is bigger than the resolution of the VLTI, light from across the stellar surface combines incurrently, and this will cause a decrease in the fringe contrast that you measure, and therefore a drop in the visibility amplitude. So the normalized visibility amplitude for a resolved source, this one here, will be less than 1. Now, for a binary system, so a binary star will produce 2 fringe packets and 1 for each star in the system. So if the separation between stars is small enough, the fringe packets from each star, they will overlap and will produce a periodic signal in the visibility amplitude. The separation between the peaks in the visibility, here in the visibility curve provides a measurement of the binary separation, and the minimum visibility here measures the flux ratio between the 2 components of your binary system. And this is exactly the type of signal that we are getting in our data. And then we have a second interferometric measurement that we call the closure phases, and it gives us the phase information. I talked too much about this, but basically, if you have a signal in the closure phases, it might vary between -180 and +60 degrees, and it gives you information about the asymmetries in the system, such as like a difference in the brightness in the 2 components. A star with a bright or dark spot with the stellar surface, there is an asymmetric disk or a disk around one of the stars. Yeah, so it gives additional information on the structure of the source. Good. So in practice, this is how it looks in interferometric measurements. So you have here the closure phases and here the visibility. For each system, so we have 6 of these because we have 6 sources, so we have 6 sets of data. And for each system, we use a modeling tool to try to recover the structure of the objects that we are looking at. So we use models for that. So we kind of built our own models to try to reconstruct either a single star, a binary star, a triple system, a quadruple system, until we are satisfied by our chi-square, which means that the model really fits well the data. And then we can say, okay, I found here a binary system, a single star, because I don't have any signal. And then you can also add more complexity, such as full risk components, disks, or whatever. So the main parameters that we measure are the position of the companions and the flux ratio between the central star and its companion. What we found in our datasets is 3 triple systems and 2 binaries. All of them having a separation range from 1.2 to 120 AU. and flux ratios ranging from 0.03 to 80%. So all of the sources are involved in multiple system, and with that we can compute the multiplicity fraction, which is the number of multiples out of the total number of objects that we observe. So all of them were found in a multiple system, so we can say that there is a 100% of multiplicity fraction. And if we account for the other companions that are found in the literature, if you remember the spectroscopic companions, then we go to a companion fraction greater than 2. We went a bit further in the investigation and tried to understand whether this multiplicity extends at younger stages and wider separations. So if I come back to this diagram here, we explored this range of separations, basically up to 120 IU. And now we want to see if we also see companions at wider separations. And if we do so, then we might have hints of one of these star forming areas. So this is what was explored in the second project. So this time we make use of just one telescope, a single dish telescope, but which is assisted by adaptive optics. So when passing through the atmosphere, the wavefront that comes from the objects is a bit distorted because of turbulence. And there is a technique called adaptive optics that consists of a series of analyses and in real-time tests to make also in real-time corrections. And this is done by basically moving or changing slightly like the surface plane of the mirror so that you will recorrect for the distorted wavefront. And the way, like the image that was maybe looking blurry at first is now really is neater and closer to the diffraction limit of the telescope. So we obtain, sorry, I think, yeah, I got to put in this. So we have now like a set of 13 young massive stars, and we are looking for companions at 50,000 AD. This is the type of images that we obtain here. So we perform some source detection in all of the images and some PSF fitting to retrieve the physical parameters of the stars, which are presented here. So when we have this kind of image, we try to spot all the different sources that are plotted here, and then we get their flux and also their position. And an important thing that we did as well was to assess whether or not these stars are bound to the central star here. For example, if I look at my mom, which is in the middle of the auditorium, I take a picture, I will have foreground people and background people. It's the same when you look at the star in the sky. You might have foreground star and also background star that has nothing to do with your the star that you're observing, and that are maybe polluting a bit your image. So you are not polluting your image. And this is done by some statistical resource because we cannot really monitor the movement of all these stars. And if they have like a probability of being fore or background source bigger than 20%, then we discarded them for the rest of the analysis. We could also, for these 8 sources, for these 13 sources, derive a multiplicity fraction. So only 8 of them appeared to be in a multiple system. So it leads us to 62% of multiplicity. And the companion fraction is also greater than 2. Here I display basically what is the distribution, the separation distribution of the companions for each system. And the separation at which companions are found can tell us about the formation path involved in the formation of massive multiples. And the two previous projects that I just presented already provide us valuable observational trainings. So, okay. So from all these properties, we can speculate as of the formation history. However, we have to keep in mind that a successful theory for multiple formation must both reproduce the observed multiplicity statistics, so the one that we see here, but can also be able to reproduce and model young and individual sources and how we form them. Sorry. So, for example, if we look at the widest separations here, it is most likely that these stars have formed through core fragmentation or capture or any other dynamical interaction, just given like the stellar parameters. So it might be interaction between different multiple systems. It might also be some partner exchange and that shifted the hierarchies. If we look now at closer separations, this companion might have formed through disk fragmentation. It is like one of the channels that can apply because we know that massive stars can have disks up to a few thousands of astronomical units. And these companions can migrate to spectroscopic orbits. I will come back to this later. Still, for this channel, we can still question ourselves like how fragmentation can form very high mass companions. For the previous project, it was conducted with gravity, so we look at even closer separations. For this fragmentation, if you look at the processes of fragmentation, this fragmentation could be a very good formation channel to form such companions. This has been tested also through simulations by teams, and they found that you can actually form close companions through these formation channels. So you might form companions in the disk. At first, they are just fragments, and then as they migrate, they also gain in mass. And if they are not destroyed by any destruction process, then they can become close companions. And finally, we cannot completely rule out capture because now we know that it also happened in low stellar density environments, and that in this kind of environment, such as M17, stellar interactions do happen. And also, in the framework of forming these companions, I don't know why there is this word here, so avoid it. There are also other mechanisms called quasi-Lidov cycle in the case of triples, because we have seen that we have more than two companions on average, so it means that there is like a third companion involved in these systems and can, of course, influence the formation of close binaries. And one last thing that we are missing in this puzzle is the influence of a close of a third companion, and this leads us to the third project we conducted, which aims at studying triple systems. And this was motivated also by the fact that in both projects we have a companion fraction that is greater than 2, so triple systems are more common than we initially thought. And for this project, we will also use again longer interferometry. Cool. So in short, in a triple system that is said hierarchical, which is stable, a tight binary is orbited by an outer companion, and they are usually in a rather stable relationship, such that they don't merge or there is no one of the components that is ejected. And in this stable situation, dynamical effects can happen. So this is like an orbital phenomenon that was developed to explain the orbits of certain planetary satellites by Lidov and Kozai in the 60s. So the Kozai-Lidov mechanism comes into play when we have at least three companions, bodies in the system. So you have two bodies that orbit each other here in the two situations. And under certain conditions, the perturbation from the distant object can change the shape of the two main object orbits here, such that you will have a period exchange or oscillations between low stages of low eccentricity and high inclination, so almost circular but very inclined orbits, or you will have very high eccentric orbits but almost aligned with the plane of the third orbit, the outer orbit, sorry. The system will be considered stable if the period of the outer companion here is at least 5 times the period of the inner companion here. Good. So in this situation, you have an inner system that is usually detected by spectroscopy because it's a very tight binary. And you have an outer companion that is detected by interferometry because the separation here is rather large. So there was like campaign that was conducted with VLTI Pioneer to try to spot this third companion. And so in the sample, in the dataset, we have 21 massive hierarchical triples. And we look for correlations between the parameters, such as like the mass of the binary, the mass of the outer companion, the separation of the inner binary, the separation of the outer binary. We also check for the stability of this system. So if they meet with the theoretical criteria of stability. And we also bring observational constraints on their architecture. Okay. So, for example, we find that more than half have a mass ratio, so between the outer companion and the inner binary, that is greater than 0.5, which means that the tertiary is more massive than one of the two components in the inner binary, which is a result that was not found before. And this has strong implications in evolutionary pathways of these systems. For example, recent worked studies show that the most likely evolutionary path, if it is the case, might be that then you have mass exchange that can be triggered by the outer companion instead of just the binary. We also looked at then the stability of the hierarchical systems. And for this, we used theoretical criteria. So it's a rather long equation that I haven't put here, but it would be like modeling. And this equation mainly relies on the eccentricity of the systems, their inclination, their mass ratio. And we find that no system is close to the stability line, which tends to show that these criteria could most likely be refined because we have here, like, no, this space here is not automatic. We have a star here that falls into the instability wall, but we still have doubts about this one, and we don't know if we can rely on the spectroscopic solutions that were found in the literature. So this project is still ongoing, and we aim at deriving the full interferometric orbital solutions so that we don't have to make assumptions on the relative inclination of between the spectroscopic orbit and the interferometric orbit, which is something that we did here. The team of Hugues has like a long-lasting monitoring program so that we can actually get some data points for the full orbit of the outer companion, and we could eventually reproduce the full orbit. So, okay, in conclusion, so we studied no less than 50 massive systems during this PhD. They were characterized by means of high angular resolution techniques. the work of this thesis has demonstrated that massive stars, even in their earlier stages, are predominantly found in multiple systems involving 2 or more companions. And we confirm against the high degree of multiplicity at young stages of massive stars. And we also show or find hints that the multiplicity is rooted in the formation mechanism themselves. Yeah, with these different scales, then we could find different properties and provide some hints about the most likely formation pathways. Good. The multiplicity of young stars was studied for 2 main reasons. The first one was to investigate the initial conditions of the multiplicity, which can affect the evolutionary pathways in the evolution, and then to understand the physical processes causing the pairing mechanisms. So the results of this thesis brought progress on these aspects. However, the work is far from being done and a lot remains to be explored. So this work could be, for example, extended to other star-forming regions in which a low radial velocity dispersion was also found and measured. And we could see whether our findings of close multiplicity also extends to other star-forming regions in our galaxy. And also, we could now go at even larger scales and try to understand the interaction between the gas or the star-forming material and the circumbinary disk, or to try to understand how we can actually form such big companions with this fragmentation. So several forthcoming telescopes and instruments present promising avenues to address these remaining gaps. On mass multiplicity, their formation, and their pairing mechanisms. I will just, among many others, mention here the VRTI with the gravity pulse instrument, and also the SGR series of instruments that is coming, and also the European extremely large telescope that is on its way. So now it looks a bit more like this. So we have to wait more years, but yeah, it's on its way. Thank you all for your attention, and I would like to take questions.
Thank you very much for this excellent presentation. It was especially great to see how in science can become such close companions. I also compliments to the artist, which I believe is the person in the center of the room. And now let's focus back to the science part. I would like to give now the floor to the examination committee. And typically the tradition is here that this will be the person who comes to furthest debate. Of course, this is a bit in the hypothetical hard to argue. This is Professor Stefan Gauss, who is currently at the University of Exeter. So please, the floor is yours. I will give you. Thank you.
Yes, thank you. Can you hear me?
Yeah.
Okay, great. Thanks, Emma, first for this very inspiring talk. This was really great. Also, it was really a pleasure to follow the progress that you made during your PhD journey. In particular, that you also use so many different techniques that are really complementary and that are, I think, really at the edge of pushing that field forward. So thanks for your persistence and for not shying away from all the challenges that are associated with using these really sometimes difficult techniques. So I wanted to ask some questions, namely first related to your observation technique. So historically, massive stars are studied typically at longer wavelengths, in particular if you're interested in the formation mechanism of these massive stars. So people often use a submillimeter or mid-infrared regime. So what are the reasons that you push to this shorter wavelengths, and can you maybe also think about some synergies from combining short and long wavelengths observations for your studies?
Yeah, thank you, Stefan. I don't know if you all heard his question. So it was, I think, to tell me if I'm wrong, but if I can a bit elaborate on observing massive stars or young massive stars with longer wavelengths such as mid-infrared and sub-millimeter facility. So yes, indeed, I mainly used near-infrared in this thesis with NACO or gravity. But indeed, use, for example, ALMA, which operates in the sub-millimeter. I especially think, for example, of observing like the CO emission that can be done with ALMA, and this basically to maybe study the kinematics of the gas that is around these binaries. We can, for example, maybe build some moment maps to see how the gas flows. And of course, yeah, going further in the wavelengths is better because we know that these massive stars, and they peak around 100 microns. So the peak of the emission is around 100 microns. So there are more luminous actually at longer wavelengths. We haven't used here longer wavelengths, but yeah, in the future, I think we can definitely go for this.
Yes, thank you. Also, some of your work was on triple systems. And in that case, you have two different orbital planes that can potentially be misaligned with respect to each other. If I understand correctly, you haven't, you don't have a system yet where you have really the full orbital parameters for both orbital planes. But did you look into how many stars you could study with such orbit alignment measurements, and can you elaborate a bit on what we could learn from that with respect to the formation mechanism?
Thank you. I will repeat again the question. So, if I'm not mistaken, he asks that I don't have full solutions for both orbits of the inner binary and the outer binary in the case of the triple systems, and if this is something we can observe or measure for some of the targets that we have in our sample. So actually, I think in the thesis book, I show, I present 4 cases for which we have reliable stereoscopic solutions, and for which we also have some interferometric solutions for the separation and the period. So when this is just 4 objects that we study out of the 21. And of course, as I explained, the stability criterion of modeling requires that we know precisely the outer ratio and also the relative inclination between the 2 orbits. So this is really something that we need to turn on. And I know that there is ongoing campaigns, and observations to keep yearly or even every 6 months data points with Pioneer. To actually measure these differences. So these separations about 2 AUs to 10 AU, I think. And we have like, I think, more than 10 years of data now. The data is mostly reduced. We really have to look into them and try to reconstruct, yes, the interferometric orbits. I had to look to this data actually, and we can do so for 12 out of the 21 cases that we talk about in the thesis.
Mm-hmm. And as part of your conclusions, you kind of made it clear that it can be difficult to rule out certain scenarios, right? Like science also often moves incrementally forward, and we often cannot give a clear answer on the one mechanism that is happening. So going ahead, what do you think will be the best experiments that we can do? Do we mainly need to increase the statistics with the techniques that we're using already, or are some of the new experiments that you showed on your last slides really able to provide completely new insights and to provide breakthroughs in that field?
Yeah. Should I repeat as well? Okay. So he said that in the end, with all what I presented is still very hard to discard between one or the other formation mechanisms. And I showed like in the future prospects what can be done. So he asked like what would be the best strategy to try to tackle as soon as possible this question, which is what mechanism is forming this type of systems. So yeah, I think it still needs to be tackled in two angles. I think it's still very important to try to assess what is the multiplicity from the very closest environments until the widest, so that we have like a whole picture. So I still think that spectroscopy is still very important because we need to know if at the young stages we have like companions separated at less than 1 AU. And I think it's very important to have like all this separation range and try to assess like the multiplicity in all this separation range. Then I think it's also very important, in addition to just study the multiplicity, also study how the gas flows, if there are like streamers that can fit the disk, because we know that these mechanisms exist, but we still have like issues on understanding how to form such massive companions around these stars. So yeah, I would still try to combine also observing campaigns at multiple wavelengths, because we can probe different physics, and this can give us hints on the preferred formation channels as well. I hope this answers your question.
Yes, thank you. Thanks for answering my questions. I'm happy to give the next examiners the floor.
Thank you, Stefan.
Thank you very much. We switch then to Professor Lex Kager from the University of Amsterdam, who should also be online with us. Thanks.
Thank you very much. Emma, first of all, I enjoyed very much your presentation and also congratulate you on the beautiful results that you have obtained on closed binaries in massive stellar populations. My question relates to the star formation process itself. As you know, angular momentum is a key aspect to that. And it is actually quite difficult to form stars, especially massive stars. And Adriaan Blauw, a professor that you may have heard of from the Netherlands almost half a century ago, he claimed that actually binarity is a fundamental property of the star formation process. And to make the question then very simple, do you think that you can form single massive stars?
Okay, I will repeat again. So Professor Lex asks if it's actually not the other way around, that binarity is a universal feature and that it's not even more complicated just for one massive star. And this is actually a very complicated question, I think. But if I think of it, there are like so many destruction processes also when you form a massive star that maybe at first you might form a multiple, but there are so many ways to actually destroy the forming companions or that they are being ejected that maybe, I don't know, there are also mergers that maybe single massive stars might have first been formed in multiple systems, but when you observe, for example, them on the main sequence, they have already undergone so many like dynamical mechanisms or destruction processes that like all the companions were gone and we just observe them as single stars. But then this doesn't really answer the question, because you ask like if we can just form one massive star. And yeah, I don't have any on top of my mind, like answering this, but I will definitely think about it.
Now, I actually think that you went very well in the right direction in answering my question, So personally, I actually would expect that star formation and binarity or multiplicity, even going down to the lower mass stars and planetary companions, that multiplicity plays a fundamental aspect there to solve the angular momentum problem. The next question that I have relates to another slide that you showed, that Makla Ramirez-Tanus published in a paper, that she looked in the radial velocity dispersion of these massive stars, and then she finds this trend that increasing the age of the population, you seem to see more and more close binaries. And now I was wondering, first of all, what do you think about this relation that she found, which is based on radial velocity studies? And would you be able to actually prove or disprove what she found using your techniques with interferometry? And this all comes down perhaps to what is the closest binary that you can still observe. But perhaps you could elaborate a little bit on this.
Yep. So I'll repeat the question again. So when I was presenting the M17 star forming region and the project about it with gravity, I showed a plot that was done by Bordier and Ramirez-Tanus, showing the radial velocity dispersion as a function of age of the cluster, and you could see this really clear trend that as the cluster gets older, then the radial velocity dispersion tends to be higher. I don't know if you really remember what is the relationship between radial velocity dispersion and close or wide binarity, but if you have like a low radial velocity dispersion, it tends to show that you have more wider binaries, and it would mean that when the cluster gets older and the radial velocity dispersion gets higher, then you have more close binaries. And she explains this by saying that the migration scenario might happen in 1 or 2 million years, so that in 1 or 2 million years, then you harden the outer companion towards the central star, so that you have a tight system. And Professor Lex Tapper asks what I think about this, and if I can prove or disprove what she wrote in her paper. So from what we did with gravity, actually a good proxy of what she says, and this theory of migration would be to spot companions within the expected size of the disk. M17 is just 1 million year old, and I think that she speculates that this migration scenario might happen on timescales of 2 million years, more or less. And we actually spot companions between 1 and 100 AU that might show that they're actually migrating inwards, and this is also in favor of what she finds. Then, as I was saying in the future works, I think we also look at the other clusters that she has on this plot to see if this is also something that we see. For example, for the ones that have the high radial velocity dispersion, do we still see companions at wide separation? And then that would disprove the theory in which they are all close when they get older. So yeah, I would say that in the end, our results align pretty well.
Okay, thank you. And my final point is the most massive stars. I think you also alluded on that already in answering my first question, that perhaps the most massive stars are the results of merging somewhat lower mass binaries. Could you say a little bit more about that? Is that actually the way we form the most massive stars?
Okay, I'll repeat. He says that, that the most massive stars might have been formed through mergers. So I think what he calls by the most massive stars are stars with masses over 60 mass, so maybe even more, maybe 100. And indeed, this is a problem also in theories of massive star formation, because we don't know how all the material can actually be accreted and form such massive stars, especially because I showed that the formation timescale is really short, so you need like really good mechanisms of accretion to build up these stars. And as you mentioned, I also agree with that the most massive stars might rather be the result of collisions between two stars, massive stars, that then merge and can create a very high mass stars. And I'm trying to think about other processes, but I think on top of my mind, I would also suggest mergers to form the highest mass stars. Yeah, I still don't fully believe that just with accretion from the disk you can build up such massive stars. Yeah.
Emma, thank you very much.
Thank you, Lex.
Thank you very much. Let me move to the persons in the room. So that will be first Professor Bordier from the University of Bordier. This will be then directly followed by Professor Denis from Canada.
Sorry, Anne-Sophie. We are trying to put you on screen. Okay, let me. It's actually that one. I think it's... I should show this one. Sorry for that.
Okay. First, I would like to congratulate you for the presentation today and your students. And also, writing much is really nice, really very precise, very clear. And that's very journey at different scales with different social methods. And even trying to connect and maybe, let's say, to bridge the gaps. The gaps between solutions and the dynamic studies, as you can imagine. And so my question may be that you have the introduction and that you think about a lot about all the future prospects that we can have. My first question would be, which observational data do you believe that the astronomers will get quite soon that could be very useful for our analysis?
Very good question.
Everything about the different
yeah, I don't know, I'm focusing myself on interferometry, but I think that this is not the easiest and the quickest. So,
what you already know,
yeah.
the different, let's say, whatever system that you know, what you know, what could we imagine to know, thinking about the observational parameters?
Yeah.
Beyond that.
Okay, so you talk about just triple systems, right? Or okay.
You're welcome.
Well, I think that all the work that has been doing in getting like actually observational constraint on these triple systems that were like basically taking one data point every year is already like a very good start to study these triple systems. The thing is that like, I think what is almost the same as I told to Lex, is also like trying to combine the different techniques that we have like a full picture of all these systems, because we look at the triple system, but we still don't know like if there are like maybe other components that can be bound around. So this could be done through direct imaging, AO assisted imaging as well, such as sphere maybe, and also to look at the closest separation wedges that has been done with spectroscopy, I think, but yeah, we also don't have like fully overall solutions for all these spectroscopic binaries, and this is also something that we should do, because if we want to study these triple systems in a very accurate way, we need both solutions for the outer and companion. And I think that spectroscopy in that sense and prospect is faster to get data from than spectrometry. On top of my, I haven't studied like I know there are a lot of triple systems or multiple systems that are all together in the spectroscopy sensitivities, and that we can also explore them just with spectroscopy, for example.
And if we take the question the other way around, and if we imagine now, what would be the use of dynamic studies that would be useful for you, maybe to give some precision about the different formation methods, or maybe to give you more constraint about your observation, because I guess there are a lot of errors around. Do you imagine that the reverse could be?
You mean like also taking like theoretical to try to observe? Yeah, I totally agree.
Yeah.
Maybe the masses is something very important, because then it could tell us about magnetic ratios between the objects, and we know that some maybe instruments are not good for this type, or they don't go for high, or maybe the system would saturate, because it's sometimes the case when we want to observe young massive stars with James Webb. So I think the mass ratios and mass distributions would be something important also for us to try to guide our patients. Yeah. Yeah, so yeah, we should really work together, theorists and observers.
And maybe a last question, if you think about, I know you speak a lot about the leader of the effects and all the other effects, you know that it's always working in 3D. Dimension. Do we know anything about 3D dimension? Do we have data about that or not? Do we imagine everything is, because finally information mechanism will be one issue to resolve, but if we know that there are information on that,
yes,
then we have some clues to detect the right information mechanism.
Yeah, indeed. What you say, I think, really it's something very important as well, because we have observational biases, and it's sometimes difficult we have this information and like problems as well when we observe. So do we have 3D solutions? I am not entirely sure about that, but just the fact that we can populate even more the orbit, then we can also constrain better the models when we try to find the orbits. So yeah.
Thank you very much,
Thank you.
Congratulations on your nice presentation and the quality of the manuscript and the work that you have done. It's really impressive. I've never seen such an entertaining presentation of angular resolution. It's amazing. About that, so if you could do interconnection between the two eyes, how far should you be from your
Oh, good question. So it's like 10 centimeters, I think. Good question. What is the angular resolution? Then I can make the calculation for you. I'm pretty sure you cannot see a chameleon on top of the.
You know, it's 20 kilometers, you said, from the eye, so
yeah.
Multiply by 20.
Yeah, true.
Yeah, so I have a question regarding the chapter 3 about so you complete that migration plus disk fragmentation is a good scenario to explain the binary properties. But you also said that this system are not fully known, not yet main sequence. So would there be anything to gain by following up this system in a short time scale, in 1 million years? And what could we do to better constrain these models?
Good. I think something very important that I haven't really mentioned also is when you form companions with the disk fragmentation, you also have kind of like spin orbit alignment. Maybe this is also something we can look into if we have like a very performant instrument, so that we can look at the operation of these companions. Yeah, then I think really we should, if we had like ourselves 1 million years lifetime, then it's really like to look if really these systems are migrating. Something that we can really transpose and compare to is like with planets, for example. Like, this is a mechanism that works pretty well, so we should maybe try to think about how it can work also with terror objects. Maybe also streamers and the gas in the disk could be a very good proxy to see if it actually migrates inwards or if it's just steady here. And say like we have these processes have to work in a very short time scales, because then once the central star has triggered the reaction and will blow the disk, then you have much less also material interaction to migrate to make the companion migrating inwards. So
Second question regarding the makeup conditions.
Yeah.
So we are close to the star. We have some shared positive usually between the speakers. I believe you developed your own tool to find all components. Do you have an idea of the rate of false positive that you will get this makeup?
Yeah, that's a very good question. No, I haven't really estimated this. I perfectly know what you're talking about, because we know that with NACO and the observation, for example, for planets, there is this paper also in which we can, if we correct for this really accurately, then we can spot maybe planets. No, actually, we don't find any close by, but I also haven't fully done the correction on the speckles, so yeah, I cannot answer you on this. But it's definitely something maybe I should look into. Yeah.
Okay, thank you.
Thank you.
Thank you. Then I would like to ask the supervisor and co-supervisor, who also play, of course, a very important role in the trajectory, not only on the scientific level, for those who don't know. Do you have any questions? Or any questions?
That can be answered in 5 minutes.
We all thought so. Yeah. So since this is, of course, a public fence, you're also invited and allowed to ask questions. Any question you want to ask? You should maybe introduce that you only get to be the one who asks a question. No?
I don't have beard yet, yes.
They don't know yet.
Thank you very much, Emma, for this pretty awesome presentation. I think you know very well I'm really interested in your work, and I want to maybe hope one day learn from you how to form peanut stars. And in that regard, can you speculate on whether maybe anything special needs to happen in order to form a binary at 1 day? Because you allude to going down to closer than a month in period.
Mm-hmm.
So does something extra need to happen to go from 1 month to 1 day, or is it just an extreme?
Oh, this I think it falls a bit more into binary evolution, which is what you do. I don't know. Yeah, I still think that the influence of other outer companions is something that can definitely help pushing down to these separations. Yet, yeah, I don't think about other specific mechanism that could help forming these peanut stars, but yeah. Maybe collisions, like, oh yeah, but it's really hard also to tell, like, if you have a model that maybe can interact with another multiple system, and all of a sudden, like, you have very I actually don't know much more about this failed stellar collisions, I would say. But
on the other hand, you would say it's very hard to form a peanut star in situ.
in
Without-
situ, I would say yes, because I won't see why they wouldn't merge instead of
Right.
staying in this steady stage of keeping such low separations.
Thank you.
Thank you very much, Emma, for the presentation. It was super nice and quite easy to understand for people who are not familiar with the topic. I have a question. You clearly showed the impact of interferometry, and I was wondering, I'm completely out of the topic, is there already project, or could we dream of a project of doing interferometry with space telescopes? And what, I guess it can be completely out of finance, and also hard to make these telescopes work together.
Yeah.
But if such an instrument exists, what could it bring to the research you are doing, and what type of new information could it bring to the system you're studying?
Okay, yeah, good. So we have already built like much pure interferometers, for example, for the observation of our supermassive black hole at the center of our galaxy. So they recreated basically a telescope of the size of Earth. Now you're really up to date with the topic, because it actually was proposed by NASA like 2 or 3 months ago to have an interferometer on the moon. And this, I think you get rid of all the atmospheric effects. So this is like really good for images. Then you have to think about which wavelengths you're thinking of. Because, for example, for the central, the massive black hole in our galaxy, it was done like in the submillimetric, and then you lose also resolution. You build like a bigger telescope, but then you increase the wavelength, so you have this kind of balance also in the resolution. So if you would create maybe an optical or near infrared interferometer from the moon, then it would be very good for us, actually, for science we can do, because you would reach such sensitivities that would allow you to see the very close environments of the stars, and maybe also reproduce images is something that we are looking at the moment. So we look very close at the stars. We rely mainly on spectroscopy, like for separations at least, and we don't have a direct image such as interferometry, so that would be also really good. Yeah. But still not doable with the actual technical.
The last question for students, I guess. Are there any questions online? I don't see them. Okay. So last chance, last call. No? Okay, then if not, we go to the presentation. Thank you. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy, and astrophysics. Emma Bordier has presented to the faculty her PhD thesis on the topic on the origin of massive spirates in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics, and Emma Bordier has defended the thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Emma Bordier the degree of Doctor in Science, Astronomy, and Astrophysics. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principle of research integrity as described in the EMEA European Code of Conduct: reliability, respect, and accountability. I close the session.
And that's your future and
It's always a pleasure to be not the first, but the second one to address the candidate as Dr. Emma. You will know for the rest of your life as Dr. Emma. So I just want to say a few words because I know that Avi has a 45-minute speech. But it's been really a pleasure to have you in the team for the last 4 years and a half. I just want to say a few things. Your enthusiasm, your quality of communication, and your sourcing the geographical presentation that you made is just wonderful. You're a talent for that. Please continue to do so. As you mentioned briefly in the acknowledgements, this has not been a very linear path, but your life is also a very not linear because you've been moving a lot. Also, even as a student, you've been to Taiwan, now you've been to Chile, came back to Leuven, so it's international. You're the most international person we've had in Leuven, certainly not the only international person, but one of the most. And it's been nice, this diversity, this approach simply that the world is a village and that you enjoy that village. I think it's great. Continue like this, you will have the world in front of you. I would say don't break a leg, but that's the other way. I was thinking for like you as a souvenir from Leuven, and usually I go and buy something for the candidate, but I really didn't have the idea, and then I thought about something. You made a thesis about the origin of massive stars, and there's also one organization that you love a lot, which is the European Thousand Observatory. And in my library, I have a book, which is a 30 years old book. These are 65 years old. This book is 30 years old. It's telling the story about the first 30 years of the European Observatory. It's been written by the first director, Ariane Blom, that Schaper mentioned. So I'm giving this to you. And the microphone.
Sorry, just, and hopefully it won't be 45 minutes. We'll see how we go. We'll see. Okay, I apologize for reading on my phone, but I want to make sure I don't miss anything out. So, Emma, first of all, huge congratulations. I am
so happy that I'm able to be here for this very important moment of your PhD journey. It's been a long time coming, and I think this wonderful presentation has just been a perfect culmination of all the wonderful work that you've done over the past few years, and it's really shown in a really accessible and beautiful way all of the great science that you've done. So congratulations not only on this presentation, on everything. You've done it. So great. At this time, I want to so those of you who don't know, I've had the pleasure of being one of Emma's co-supervisors throughout my PhD. I came to this role pretty junior myself. You know, I just finished my PhD at the University of Leeds, and I came to Durban. And while I was excited to step up to the role, you know, I'd be lying if I said I wasn't a bit scared. You know, I'd be learning how to supervise a PhD student on the fly. I was kind of like worrying about questions like, oh, like, you know, what am I going to get on, or like, you know, what if she just thinks I'm an idiot? Like, you know, there's lots of this kind of stuff going on in my head. But it turned out, you know, very quickly after meeting you, I had absolutely nothing to worry about whatsoever. It became evident very quickly that working with you was going to be a wonderful experience. As you've already mentioned, like, you just got on with enthusiasm for everything that you do, for your work, for collaboration, and for everything. And you've been a very diligent PhD student. You know, you've had an attention to detail that I, as a very distracted person, I really envy and look up to about you. And you take great care in the work that you do and the results and the way you present them, and that's really, really a great thing to see. It's evident as well in the 3 excellent projects that you presented to us today, and the papers that you make up your thesis and the one in production as well. And you've already received a really nice amount of attention for this work. I think it's a testament to its quality and to creative stuff that you've done. So it's getting attention here in Europe also beyond. So congratulations for that. I want to emphasize again that Emma has achieved all of this and done a huge amount in a kind of quite an unusual PhD journey. Not of your own, it's been a bit of a roller coaster. You know, like you were affected by the pandemic, like many students in the first instance. We had the additional kind of complexity of having to move 11,000 miles away during that pandemic. There was obviously some delays in this, and you know, it was a very tricky situation, and you dealt with it with you know, add to this instance, like COVID, first international conference, you know, getting your laptop stolen in Chile, practically breaking your arm in practice and definitely breaking your leg in Bolton. So, like, this is a lot of stuff that the average PhD student does not have to deal with. And yet you, throughout all of it, you remained positive, resilient, you did excellent work despite all of these things. I mean, if I had to do one of those things, I feel like I wouldn't have it as well as you. So, to me, really quite a superhero in my eyes for producing such fantastic thesis, in spite of all these odds along the way. Also, I want to commend you not just for your academic work, but for everything else you've done on top of it throughout your PhD journey. You know, you've been heavily involved in both social and scientific activities outside of the PhD. I currently work at ISO in Chile, and I visited there while Emma was doing his trip out there as well. And when I arrived, I was like, oh yeah, you know, Emma is everyone who I would say that to would immediately start singing her praises, you know. So she really had a really wonderful impact on the people she met in Chile. You know, you work with organizing journal clubs, you're helping organize wine and cheese socials, and my friend, well, our mutual friend now, who was a fellow on site at the time, he was like, yeah, Emma really is like the queen of the students, you know. And it was true. I mean, like, you had such a positive, wonderful influence throughout that campus, and I think it was just really lovely to see. And so thank you for always being open, kind, helpful in any scientific environment you've been in, whether it be in Santiago, whether it be, you know, through organisation, through volunteering, or through teaching and working, house studies, everything is. So all in all, I would like to say it's been a pleasure, and it really has. I can't have imagined a much more positive experience for my first PhD student, so it's just really great. We may have started as a supervisor student, but I now see you as an esteemed colleague. I look forward to working with you in the future, and also as a friend, and I hope we can catch up on more differences. few other times as well. And it's been really fun to share Journey with you, whether we're doing scientific discussions, exploring Japan, conferences, or barbecues in Santiago. It's all been great. So congratulations again, and all my best wishes on this special day and all your adventures happening otherwise in the future. Congratulations.
Thank you.
And I have some presents. Okay, so first it's a throwback in case you're missing Pisco Sours in yogurt. Here we have premix. And then we have the Pisco real. Yeah. In case you're missing Pisco as well.
I will make Pisco Sours. I don't like Pisco Sours.
Oh, okay. And sorry. And here is a little something. Here is a little something that you're timing and writing. So this is for some of the stuff you can do in review. And this is just a little kind of memento. So as you said, you've gone many places throughout your academic careers to this point. And there's an answer I know in Leeds. I asked you to do a commission to just kind of pull in those places, which many could fit into a little memento for you. So
Thank you. Thanks a lot.
so yeah.
I guess now is my time. I don't have really a speech. I think I might go to the reception and maybe like it would be easier to talk after some beers and translation. Whatever. I would just like to say that it has been a great journey. When I see like diversity of people here, so from the university, from Chile, from CrossFit, from also my neighbors that we met, and the really nice community I had outside of academia, and this is really nice. So thanks to all of you, also for online, to my family that puts to the trip from Albania, that is very far away, and of course a big thanks to my supervisors, also William, that he's not here, but I really enjoyed working with him at ISO, and the members of the jury also, because the final work has been much improved thanks to your comments and feedback. So yeah, thanks to all of you, and I think that the reception is waiting, so that's good. I have also some reasons for the supervisors, also for William. I hope you can keep it to that. William is online. Wow. Hi, William. Thanks a lot for all the supervision at ISO, and I'm kind of sad that you cannot celebrate with us here, but thanks a lot. Good, so I think that we can stop here and go to the reception. Thanks a lot.